In section 2, we are actually going to break it down into two parts. We're going to talk about solving quadratics by factoring, and then we're going to talk about solving quadratics by completing the square. So first, we're just going to review what a quadratic equation is. So that's an equation in the form ax squared plus bx plus c. So that is our quadratic equation. Now, when you're solving a quadratic equation, you must always set it equal to 0. Because when we're solving a quadratic equation, we're looking for when it crosses the x-axis. So we're solving for when does x equal 0. So there are x-intercepts, our roots, our solutions. There's a lot of different terms for it. So let's go ahead and do some examples where we solve a quadratic by factoring. So our first problem is x squared plus 10x plus 16 equals 0. So what I'm going to do is, because it's already equal to 0, I'm going to go ahead and factor the left side. So I'm finding what multiplies to 16 and adds to 10. And that is positive 8 and positive 2. So I get x plus 8, x plus 2 equals 0. Now what I do is I take anything that contains an x and I set it equal to 0. So I have to do x plus 8 equals 0. And x plus 2 equals 0. And I solve both of those equations. So the first one, we're going to be subtracting 8. The second one, we're going to be subtracting 2. So that gives me that x equals negative 8 and negative 2. In our second example, we have x squared minus 9x equals negative 18. So before I can put it in factored form, I have to get it equal to 0. So I'm going to add 18 to both sides. So we get x squared minus 9x plus 18 equals 0. And now I can figure out what multiplies to 18 but adds to negative 9. And that's going to be negative 6 and negative 3. So I have x minus 6, x minus 3 equals 0. So now we do x minus 6 equals 0 and x minus 3 equals 0. So I'm going to be adding 6 and adding 3, which gives me that x equals 6 and 3. Our third example says 3x squared equals 11x plus 4. So I have two things that I have to subtract. I have to subtract the 11x and I have to subtract the 4 from both sides. So we get 3x squared minus 11x minus 4 equals 0. So because my number in front of x squared isn't 1, I would first look for GCF, which there isn't 1 here. So that means I'm going to have to factor this using my box method. So we have 3x squared and negative 4. So what I'm doing is I'm looking for the multiples of negative 12 that add to negative 11, which are going to be negative 12 and 1. So we have negative 12x and we have 1x. So when I factor out my GCFs from my rows and my columns, I get 3x and 1. And x and negative 4. So my factored form is 3x plus 1, x minus 4 equals 0. So we're going to do 3x plus 1 equals 0, and x minus 4 equals 0. Now the x minus 4 equals 0 is easy. I'm just going to add 4. Now for the 3x plus 1 equals 0, I'm going to subtract 1, but that gives me that 3x equals 1, and then I have to divide by 3. So I have 2 steps. So that's going to give me the solutions that x equals 4 and 1/3, which you're going to always leave our solutions in terms of fractions if you don't get a whole number. You are never going to use a decimal when solving by factoring. Our fourth example, we have 9x squared minus 25 equals 0. So this is an example of a difference of squares, because 9x squared is 3x times 3x, 25 is 5 times 5. So it's going to factor as 3x plus 5, 3x minus 5, and then equals 0. So we're going to do 3x plus 5 equals 0, and we'll do 3x minus 5 equals 0. In both cases, it's going to be a two-step process. So for my first equation, I'm going to subtract 5, so I get 3x equals negative 5. Then we're going to divide by 3. For the second equation, we're going to add 5, so we get 3x equals 5, and then we're going to divide by 3. So we end up with the solutions x equals negative 5/3 and positive 5/3. So when you're solving a difference of squares, you're going to get the same solutions, just one positive and one negative. Just like when you factor a difference of squares, you're going to have the same thing in both sets of parentheses, just one is a plus and one is a minus. In our next example, we have x squared minus x minus 12 equals 0. So I'm already equal to 0, so I can go ahead and factor. So I'm looking for what multiplies to negative 12 and adds to negative 1. And it's going to be negative 4 and positive 3. So then we'll do x minus 4 equals 0 and x plus 3 equals 0. So we're going to add 4 and subtract 3. So we get x equals 4 and negative 3. And then in our last example, we have x squared equals 100. So again, I have to be equal to 0, so I'm going to subtract 100. So we get x squared minus 100 equals 0. This is another example of a difference of squares. So x squared is x times x. 100 is 10 times 10. So it factors as x plus 10, x minus 10 equals 0. And we solve for x plus 10 equals 0 and x minus 10 equals 0. So we'll subtract 10 and we'll add 10. And we get x equals negative 10 and 10. So let me know if you have any questions about solving a quadratic by factoring. The second part of section 2 is solving a quadratic by completing the square. So completing the square can be used if a quadratic isn't factorable. It can also be used when a quadratic is factorable. So we can use the completing the square in a lot of different ways. When we are completing the square, the goal is to make the left side of our equation a perfect square trinomial. So what that means is if you have something that's x squared plus bx plus c equals 0, it factors as the same thing in both sets of parentheses. So that could be x plus, we'll give it another variable. Let's do x plus p squared. So what that means is you have the same thing in both sets of parentheses. So that means that your constant c is a perfect square. So 1, 4, 9, 25. And that when you add it to itself, you get your b term. So for completing the square, it does have a lot of steps in the process. So the first step in the process is to always move your constant c to the other side of the equation. So whether that means adding or subtracting c to the other side, we always move that constant over to the other side, because it is not necessarily, when we do completing the square, not necessarily going to be a perfect square already that works with our equation. The second thing, which is probably one of the most important things in completing the square, is that we can only use completing the square method if a is equal to 1. So that means that you have to have an equation that is just x squared. And if a is not 1, you have to divide everything by a to make it 1. So that's probably one of the most important steps. The third step is how we get our perfect square trinomial on the left side. And the way we get that perfect square trinomial is we add b divided by 2 squared to both sides of the equation. Because if I'm going to add it to the left side to make it a perfect square trinomial, I also have to add it to the right side, so I'm not changing the original equation. Now you're going to factor that left side. It's going to be a perfect square trinomial, and it always factors as x plus whatever b divided by 2 was, and then squared. And then the last step is to finish solving by taking this square root. So it's kind of hard to understand completing the square with all of the steps just written out, so we're going to do a couple examples so you kind of get an idea of how completing the square works. So for our first example, we have x squared plus 2x minus 35 equals 0. So my first step here is going to be to move that 35 to the other side. So we end up with x squared plus 2x equals 35. I don't have to do step 2 here because a is 1 already. I just have my x squared, so I don't have to worry about dividing by anything. So now I'm going to go to step 3, which is adding b divided by 2 squared to both sides of the equation. So b in this case is 2, so we have to do 2 divided by 2, and then we have to square it. So 2 divided by 2 is 1, and 1 squared is 1. So I'm going to add 1 to both sides of the equation. So I get x squared plus 2x plus 1 equals 36, because 35 plus 1 is 36. Now I'm going to factor that left side, so it's going to be x plus, and then b divided by 2, so 2 divided by 2 is 1, squared equals 36. Now I'm going to take the square root of both sides, because that's how I'm going to get rid of that squared, so I can solve for x. So I'm going to get x plus 1 equals, now here's where we get 2 solutions, because we saw in part 1 that when we were solving by factoring, all of our quadratics had 2 solutions. So far, the way I'm working through our completing the square method, if I just took the square root of 36 and said it was 6, I wouldn't get 2 solutions. So we have to think back to last module when we were talking about square roots, is that every number technically has 2 square roots, positive and negative. So the square root of 36 is actually going to be plus or minus 6. Because if I do a positive 6 squared, I'll get 36, and if I do negative 6 squared, I'll also get positive 36. And then my next step here is going to be to move that 1 to the other side by subtracting it, and we're going to get x equals negative 1 plus or minus 6. I cannot subtract that 1 from 6 and write plus or minus 5. That is not how this works. Now, since the square root of 36, it was a perfect square, and I got an actual number here, I can go ahead and find my 2 solutions. So negative 1 plus 6, which is going to give us 5, and then x equals negative 1 minus 6, which is going to give us negative 7. So my solutions are going to be 5 and negative 7. So I could have also factored this quadratic, and I would have gotten the exact same solutions as completing the square. Our second example, we have x squared plus 8x plus 10 equals 0. So my first step here is I'm going to subtract 10. So we have x squared plus 8x equals negative 10. Now I'm going to do my b divided by 2 squared since a is already 1. So we're going to do 8 divided by 2, and we're going to square it, which is going to give us 4 squared, which is 16. So we're going to add 16 to both sides. We're going to get x squared plus 8x plus 16 equals 6, because negative 10 plus 16 is 6. When I factor my left side, I'm going to have x plus, and then 8 divided by 2, which is 4, squared equals 6. Take the square root of both sides, and my left side becomes x plus 4, and then equals plus or minus. Now I'm going to look at the square root of 6. I can't simplify that. 6 is not a perfect square, and I can't break it down and bring any numbers outside of the radical, so it's going to stay the square root of 6. And now I'm going to subtract 4 from both sides, And we're going to get x equals -4 plus or minus the square root of 6. And I'm not required to write this as two separate answers. I can leave it in this form, and that's going to be my answer. And we can't actually solve for what x is because the square root of 6 was not a whole number. So for our third example, we have x squared equals -6x minus 10. So my constant is already on the right side, but so is my x term. So I actually want to move that 6x back over to the left side. So then we get x squared plus 6x equals -10. And a is already 1, so I can go ahead and do b divided by 2 squared. So we're going to do 6 divided by 2 squared, which is going to give us 3 squared, which is 9. So we get x squared plus 6x plus 9 equals -1. When I factor my left side, we'll get x plus 3 squared equals -1. We're going to take the square root of both sides. So we get x plus 3 equals plus or minus. Now we just talked about in section 1 how if you take the square root of a negative number, you end up with a complex number. So we know the square root of -1 is I. Now we're going to subtract 3 from both sides, and we're going to get that x equals -3 plus or minus I. And that's going to be our final answer. Let's go ahead and take a look at an example for when a is not 1. So we have 4x squared minus 2x minus 5 equals 0. So my first step is going to be to add 5 to both sides. So we get 4x squared minus 2x equals 5. Now before I can add b divided by 2 to both sides, I have to divide everything through by 4 because my a value is not 1. So when I do that, I get x squared minus 1/2 x equals 5/4. And it is going to work better for us if we leave everything as a fraction and don't write any decimals. Now I can do my b divided by 2 squared. So I have to do -1/2 divided by 2 and square it. And when I do -1/2 divided by 2, I get -1/4, which when I square gives me 1/16. So we get x squared minus 1/2 x plus 1/16 equals, now in order to add 5/4 and 1/16, they need to have the same denominator. So 5/4 I can get as a denominator of 16 by multiplying the top and the bottom by 4. So 5/4 is the same thing as 20/16. So when I add 1/16 to that, I'm going to get 21/16. And when I factor it, so my left side is going to be x. Now instead of it being plus, in this case, b divided by 2 is going to be negative. It's -1/4. So I'm going to do x minus 1/4 squared equals 21/16. We're going to take the square root of both sides. We get x minus 1/4 equals plus or minus. Now when it comes to simplifying the square root of 21/16, I can treat that as the square root of 21 over the square root of 16. And I can't simplify the square root of 21. It's not a perfect square. It breaks down as 7 times 3, so there's not any numbers I can bring out. But the square root of 16 is 4, so I can go ahead and simplify that. And then my last step would be to add the 1/4 to both sides. And we end up with x equals 1/4 plus or minus the square root of 21/4. I am not going to have you do a lot of problems where you're going to be dealing with fractions. But it is important for you to see how a completing the square problem works when a is not 1. So that leads us to the last part of the notes, which is when does completing the square work well and when does it not work so well? So it works well when a is 1 and b is even. Because if you think in terms of if b is not even, if my number in front of x isn't even, when I go to divide it by 2, it's going to end up with a fraction. So we're not going to just specify that's even, but it's also a whole number. Because we saw in our previous example, even though b was even and it was 2, but when I divided through by a and I got 1/2, 1/2 is technically an even number, but then I had to divide it by 2 and it still stayed a fraction. So completing the square works well when a is 1 and b is an even and whole number. So it doesn't work well obviously when a is greater than 1, because then you have to divide through by 1, but a is greater than 1 and a is greater than b. Because if we just saw in our last example, even though b was even, a was bigger, so it gave me a fraction. If b had been bigger than a, and I divided through by 4, it could have still been a fraction, but there's a higher chance that it would have been a whole number as well. So we want to make sure we're going to use completing the square most often when a is already 1 and b is an even and whole number. So even if a weren't 1, but a was maybe like 2, we'd want to make sure b was an even number and a whole number so that when we divided through by that, it wasn't so bad. So let me know if you have any questions about completing the square, whether it's a specific step or all of the steps or just questions about why we did some things.